Okay, well, thank you. So I'm going to be talking about these other things in space, and especially I want to talk about gravity, which is the most important force in the universe. And I'm going to be talking about how we can use gravity to actually go to the planets, for missions, and most importantly, how we calculate those orbits. So let's start from the beginning. At some point, really long time ago, people were looking at space and they were looking at these stars and these planets, and they were trying to figure out how they move. And everything was a bit messy. They created some models, but they were overcomplicated. And at some point, Copernicus came and said, "This is too complicated. If we put the Earth in the middle, I don't like this. This is not how it's supposed to work." So he said, "What about we put the sun in the middle, and suddenly everything looks really smooth, really nice." He said, like all the orbits are not circular, everything works out. So this was a great. So good for Copernicus. And then Kepler came and he said, well, actually, orbits are elliptical and the sun is located in the ellipse. Additionally, I can tell you, just from looking to the sky, that the planets move faster when they are close to the star and they move slower when they are far away from it. And also, third law, I can tell that the time it takes for a planet to go around the star is only dependent on the size of its ellipse. So he was like, no, this is great, I'm done. Newton came and he said, well, now this is great, but now I found a mathematical formulation that is going to unify all these laws that we know, and he found his universal law of gravity. So what he said is, now we know that the force, the gravitational force that attracts one body to another, is proportional to one constant, and most importantly to the masses of these bodies. So if we have two big stars, they attract each other more than if they are small, and if they are far away, then they attract less than if they are close. Really easy. So he said, well, now we have solved the universe. Now we have everything done, we don't have anything else to do. So, enter Einstein. So Einstein said, actually, you might want to do some corrections because general relativity tells us that if you're really close to something really big, then, well, Newton's equation is not going to stand. So, yeah, this helped a lot because it's helped to solve the orbit of Mercury. Suddenly we know why Mercury is sorted the way it is, why it's doing weird stuff. But there's not a similar problem. So, we like classical mechanics, so let's just go to classical mechanics for now. Newton is back. Now, what happened next? Next, the biggest problem to solve after Newton has solved everything was the free-body problem. So please remember to use in the background. So the two-body problem means that we have two bodies in the problem. And this is easy, straightforward. Kepler gave us some equations that we can use to solve it, that we can use to calculate if we know where these stars are now, if we know what velocity they have. We can know when they are in 2 days, we know when they are in 100 days, and we know when they are in 1 million days, and we know it immediately. A couple of equations, pen and paper, we can do it. Now, the problem is, when we have a free-body problem, now there's a mass, a third mass. And what happens is that now it's not only that we have two bodies attracting each other, but mass 1 is going to attract mass 2, mass 2 is going to attract mass 1, mass 2 is going to attract mass 3, mass 3 is going to attract mass 2, and we get it. So this gets a bit challenging because if we move one of the stars a bit, it's going to affect the trajectory of the other two a lot. So this means that, well, we don't have easy equations for it, and actually it's been theorized that we can prove that we can solve this problem analytically. We are not going to find a solution to solve it. So what we need to do is solve it numerically. So I'm just going to say really briefly, what we do then is we divide the trajectory into small pieces that we're going to call small steps, and then we're just going to do the trajectory really little by little. And I'll just mention this now and call it later. But for now, main idea, two-body problem, easy, analytical, we like it. Three-body problem, we cannot solve it analytically, we need to solve it numerically, and it's chaotic, which means that if we change a bit where the first star is in the initial conditions, by the end, our problem is going to be completely different. So this is also a big problem. So now, end of introduction. Well, forgot about saying, a really important free-body problem is sun, Earth, moon, and that's why we really care that the universe is full of free-body problems. So we do care about this because it's just complicated. So there's a special case for the free-body problem. The next thing is a bit easier. which is what happens if in case of having three big stars, mass 3 is actually a small spacecraft. Now, a small spacecraft, instead of having a mass 3, it's going to have mass 3. So, mass 3 is actually not really going to affect the movement of the stars, right? The stars are going to affect the spacecraft, but the spacecraft is so small that it's not really going to attract or have an effect on the stars. So this simplifies things a bit. Still, we like the two-body problem better. Now, how do we get to other planets? Or better said, how do we calculate how to get to other planets? So let's just assume that our spacecraft has launched from the Earth on a rocket. There's a lot to say there, but I'm not going to say anything about it. And we have positioned in an orbit around the Earth. And of course, this orbit is elliptical, because we said that orbits in space are in general elliptical. And our spacecraft is just positioned there. We have a two-body column with the Earth in the middle and the spacecraft going there, so this is really nice, really easy like this. The problem is that, well, we can assume that it's like this because we have a thing called the sphere of influence. And this is just an imaginary sphere where we assume that inside of it, if we have a spacecraft orbiting inside, we can assume that what is affecting it most is the Earth, because as we said, the effect of gravity depends on distance. So as long as we are orbiting the Earth quite close by, the main gravity that is going to affect us is the Earth. The reality is that the Sun is actually there. It's far away, but it's there. So what is going to happen is that now we have a two-body problem, and this effect of the Sun is going to make our orbit a bit wobbly. Again, we're inside the sphere of influence, so to calculate our orbit, we don't really need to calculate the effect of the Sun. Now, we have the Earth is orbiting the Sun, or spacecraft is still orbiting the Earth. And how do we calculate if we want to go to Mars? So what we're going to do is relate the two-body problem instead of the three-body problem. So what we're going to do is we're going to try to find the trajectory around the Sun that takes us from the Earth to Mars. And then we only need to take into account the gravity of the Sun for our spacecraft. Okay, so in order to do this, what we need to do, we need to change from an orbit around the Earth to an orbit around the Sun. What does it take? That takes fuel, energy, however you call it, right? So we need to turn on our engines, give some energy, and suddenly we've moved out of the sphere of influence of the Earth, and we are in an orbit around the Sun. We arrive in Mars, and then again, we enter the sphere of influence, we put our engines, and this time we put the engine to the different direction, and we enter the sphere of influence of Mars, and we start orbiting Mars. That's what we do. Now again, the Sun is there, but we're not taking into account because we like to do that before. So all these calculations can be done with pen and paper because they are just two-body problems, elliptical orbits around the Sun, around the Earth, and Mars. So that's all. The problem is that going to Mars, that we've done, that with one ellipse, with one orbit, that is fine. But the problem is if we want to go to, for example, Jupiter. So what happens here is that I said that we need to apply turn on our engines if we want to go from an orbit around the Earth to an orbit around the Sun to get to Mars. And the problem is that that engine needs to be switched on, and it needs to give us a change in velocity of 2.9 kilometers per second. And now that means nothing to you, but maybe it means something if I say that in order to do that to go to Jupiter, it would take us 8.8 kilometers per second. So the problem is that 8.8 kilometers per second is not doable right now. We don't have rockets that will give us that velocity. We cannot fill our spacecraft with fuel because we actually want to do like with cameras and like instruments and things like that. So this is not doable. So we cannot really do this orbit directly to Jupiter. So how are we going to get to Jupiter? Yeah. Well, instead of using our fuel, we can also use gravity. So enter gravitational assists or slingshots. So this is a way we can use gravity to actually accelerate or decelerate our spacecraft. So for example, imagine that our spacecraft is orbiting the Sun, it's just going on this orbit and it suddenly gets close by Jupiter. So we can, what happens is that Jupiter is going to start attracting our spacecraft, and that's going to curve our trajectory. So if we do it like this curve of the trajectory is in the same direction as Jupiter is moving, because Jupiter is also orbiting the Sun, right? So we can use this velocity of Jupiter to actually speed up the trajectory. And we can also use this to change our inclination or to change the direction of our spacecraft. We can do many things with it, but mostly we want it to speed up. Now, if we wanted to accelerate, we can do the same, but we just enter from the wrong side. So now, the gravity of Jupiter is curving our trajectory in one direction, but Jupiter is moving in the other direction. So that's use of the vectors. That means it's going to accelerate. So this is really useful because, for example, if you look at the transfer of Cassini, you see that it looks very similar to what we've done. You're just patching different ellipses together, and in the intersection between them, you just have a gravitational system on Venus first, and then you accelerate, and you go to Venus again to accelerate a bit more, and at some point you use Jupiter to finally get to it. So if you reproduce as well, use as recently done a really historical description of gravitational analysis because it's like Earth and the Moon together in one time, and that's quite new, really exciting. So we can use gravity to actually save the field. Now, reality is that we cannot, well, we have just used elliptical orbits, and we have just assumed that the only thing we care about is that the sun is attracting us with its gravity. But the truth is that we should also take into account that the Earth is also attracting the spacecraft and changing the orbit. And Mars is also affecting us, right? Like it's also close by, we're getting there. And the truth is, Jupiter is also quite big, so we should probably take into account the gravity, and Saturn is also around, so we should also take into account that the gravity is going to affect us. And let's not forget radiation pressure, because as I said, gravity is the most important force, but radiation pressure from the sun can also affect the spacecraft. And there are asteroids and things going around. Normally, we don't care that there's some dust or some asteroids, we should also take that into account. Let's not forget that the center of the galaxy is full of stars that can also influence our gravity. Normally they don't, but we should take it into account. And we are getting to planets, so atmospheric pressure and friction from the atmosphere, we should also take this into account. And we still shouldn't talk about Einstein. Probably we should talk about Einstein, right? Like if we get close to the sun, we should actually add relativity effect. So the truth is that we have created or calculated an initial trajectory because we like that it's quick, but reality is actually an invalid program. So, as I said in the beginning, we need to calculate this and we don't have equations for it, but like we don't have analytical equations to solve it. So what we're going to do, what I'm going to do is just divide this trajectory into what I call steps. So what I'm going to do is I first know what this spacecraft is, and I'm going to calculate all these forces that are affecting it. So like the gravity from Mars, the gravity from Jupiter, I'm going to calculate everything that is affecting my spacecraft. And from the forces, I can integrate numerical integrators. And then I can go into acceleration, and for that, the velocity. So now I know how to move from this step to the next one. So I move a tiny bit. And then I calculate my forces again. And then I make the corrections that I need, and then I move a tiny bit, and then I make my corrections again. And then I'm just going to repeat this a lot of times until I arrive to Mars or wherever I want to go. So, this is how we actually calculate also the movement of stars and the movement of planets. It's not only for spacecraft, this is how numerical integrators work. And what happens is, if we choose really small steps, then we're going to get a really accurate orbit, because then we're calculating the force a lot of times. But that means as well that we need to calculate the force a lot of times, so that's going to take a lot of time in our computers. On the other hand, if we choose these really big steps, that's really quick in our computer, but that means that we're not calculating the forces that are affecting us that often, so our orbit is going to be less accurate. So it's a choice. And now, so I just want to finish with some final thoughts. First of all, again, the two-body problem has an analytical solution and it's fast to calculate, which is something very important. And the two-body problem that has no analytical solution. And one thing that I haven't mentioned is like if we, for example, want to calculate for the movement of a cluster of stars. If we have 3 stars, we don't care. But if we have 1 million stars, at each step, we have to calculate the effect of each force and all the other million stars in the system. So this is really computationally expensive. So the larger the n body problem we have, the more expensive it's going to be. And finally, numerical integrators. I haven't seen much about them because there are too many of them. We've been developing them for years and years. We have numerical integrators for many different cases, for different kinds of scenarios, for you like this better, I like this one better, just personal taste. And they have been really made efficient, they have been all kinds of codes. The thing is that in astronomy, every time we want to do larger calculations, we want to calculations that instead of going to 1 million years, we go to like 10 million years, which means that we need either more computation power or more efficient numerical integrators. So my final thought, because I love with artificial intelligence, is that we have new tools that are coming in the field, like artificial intelligence, to actually help make our integrators a bit faster, so that we can do more accurate and faster integrations. And with that, I will take the questions.
Very loudly?
Yes.
So what kind of, how is your, what kind of AI are you using? Are you trying to optimize some mathematical calculations? Or are you doing a search between different kinds of, are you trying to find new ways to do calculations? In what way are you?
I'm trying different things. One of them, the main thing that is being tried now, is to try to substitute, so we have this equation with Newton, and you calculate all the forces that are affecting the system. So you can try to substitute this calculation with machine learning, so instead of calculate this, you predict it. So you basically substitute the integration. Another way is to use machine learning to kind of help you choose what integration you choose, like Germany or
when you integrate along the path, does it make sense to change the size of the step? For instance, if you are far away from large bodies, maybe you can do bigger step?
Yes. There are different kinds of integrators. Some of them are called fixed size integrators, so they have the same size of the step, but most of them, they have a variable size. So then if you are really close to a value that is affecting you, you want to do really small steps to really capture the change in this changing the forces that are affecting you. And if you are really far away, you want to optimize your computer time, so you want to do larger steps because things are not changing in time. So you have a lot of variable types of integrators.
What are you comparing the results of the models? Is it mostly like other theoretical computations, or maybe are you taking some real trajectories of the real missions?
So when you say all of theoretical calculations, you mean all of numerical calculations? Depends. What I do, I just do simulations. So I just calculate, whenever I do something new, I just calculate it with some other integration, some other simulations that are a bit more, they have been tested, they are more good. But you can always test it. If you are really doing some simulations, many times it's useful to compare with observations to make sure that you do the same.
Also, you're using some kind of labeled data set to compare your performance of your AI system. Do you use this known data set with the equations, or would it make more sense to make them understand equations so that we focus on?
So what did you say? It would make more sense to?
Would it make more sense to have this reference data be produced by Einstein's equations?
I'm not sure that that's true.
Einstein versus Newton.
It's different things. So it depends on what you want to do, right? Like if you just want to understand the dynamics of a certain set of values, then maybe it sometimes makes sense to only calculate classical dynamics. Whereas if you really want to calculate a more realistic scenario with black holes, for sure you need to include Einstein's equations.
I mean, for the training of your AI.
For it. So I normally generate label data using my own simulations. So you can also do simulations that include Einstein's equations and create the label data with those equations. So you can do that. Again, it depends on what you want to do, right? If you're studying a case in which relativity is not very relevant, you just want to understand the use of machine learning for that, there's no need to include that. If you want something more realistic, then for sure you should include that.